The human body is 45 to 75% water. So let's look at the factors that determine where you are in that range. The first factor is age. And in age, the younger you are, the higher your water percentage. In fact, babies win the prize for the most water. Babies are at 75% water. Think about that. A newborn baby is 3/4 water. Elderly win the prize for the lowest. An elderly person is at that low end, 45% water. Another factor that goes in is body composition. And here we're looking at lean and obese. So if you're obese, you have a lot more fat or adipose. And remember, fat is hydrophobic. So fat and water repel each other. So the more fat you have, the less water you have, because all that fat is repelling water. So somebody who's lean has a higher water percentage because they don't have the adipose to repel the water. And then the last one is sex. And in this case, men have more water. If you take a man and a woman that are the same age and either both lean or both obese so that you have an apples to apples comparison there, the man will have more water. The reason for this is that women have estrogen. Estrogen causes the growth of adipose. When a girl goes through puberty, she gets more adipose on her body. So estrogen stimulates adipose growth. And as we already talked about, adipose repels water. Men have testosterone. And testosterone stimulates muscle growth. And muscle is very high in water. So the more muscle you have, the higher your water percentage. So now we're going to look at how all this fluid, along with the electrolytes that are in it, is distributed throughout your body. So in the book, you read about the rule of thirds. So that summarizes the distribution of the water in your body. First, we're going to divide into two main categories. You're going to have intracellular, inside your cells. So ICF is intracellular fluid. This is what is inside your cells. This is also called cytosol. Cytosol is the water inside your cells. This is 2/3 of all the water in your body. So these rectangles are drawn to scale. So from here to here, that is 2/3 of the entire rectangle. Then you have extracellular fluid, ECF. So ECF stands for extracellular fluid. This is all of the fluid outside your cells. This is 1/3. So from here to here is 1/3 of this rectangle. So of all the water in your body, 2/3 of it is inside your cells, 1/3 of it is outside your cells. ICF inside your cells, ECF outside your cells. Then this can be divided into two more groups. So ECF is divided up into two more groups. You have interstitial fluid. This is all the fluid that's just between your cells. And you have your blood. If we look at how ECF is divided up between interstitial and blood, so keep in mind here, interstitial and blood are the two parts of ECF. Interstitial is 2/3 of ECF. So it's 2/3 of extracellular. So interstitial, which is also called tissue fluid, this is the water between your cells, is 2/3 of that 1/3. Well, if you multiply your fractions, you just take 2 times 1 is 2, 3 times 3 is 9. That is 2/9 of all the water in your body is your interstitial fluid. Blood is 1/3 of extracellular fluid. So all the water in your body, 1/3 of it is extracellular, and of that 1/3 that's extracellular, 1/3 is in your blood. So blood is 1/3 of 1/3. 1 times 1 is 1, 3 times 3 is 9. So 1/9 of all the water in your body is in your blood. So that's the distribution of water. Now let's also look at electrolytes. Remember, think back to chapter 2. You first learned about electrolytes in chapter 2. They're in your food, right? Calcium, sodium, potassium. Those are all components of food. So you get your electrolytes by eating food. And remember, electrolytes dissolve and dissociate in water to produce your ions. So now we're going to look at these. Inside your cell is where you have the majority of your potassium, your phosphate, magnesium, and you have proteins inside your cell. Now remember, you've learned about sodium-potassium pump. So we have a sodium-potassium pump here. That's why potassium is inside. The pump pumps it in. And remember, it's a sodium-potassium pump. So if it's pumping potassium in, it's also pumping sodium out. So here in your extracellular fluid, you have sodium. You also have calcium, bicarbonate, and chloride. Those are the main components of extracellular fluid. Blood has sodium, calcium, bicarbonate, chloride, and proteins. So now let's look at some information comparing these areas. Inside the cell, the interstitial fluid, and the blood. So which two fluids have protein and why? Well, you can see that your intracellular fluid has protein and your blood has protein. So ICF, the reason there's proteins inside your cells is because cells have ribosomes that make proteins. And the reason there's protein in your blood is because your liver, remember chapter 18, your liver makes plasma proteins and puts them in your blood. Also, chapter 22, your liver makes complement, part of the immune system, and puts those proteins in your blood. So your blood gets proteins from your liver. It gets plasma proteins and complement from your liver. Okay, so the one with little or no protein is interstitial. The reason for this is it has no source of protein, And the proteins that are in the cells and in the blood can't cross the cell membranes and the blood vessel walls to get to the interstitial. So the proteins in cells can't fit through the cell membrane to get out. And the proteins in blood can't fit through the capillaries. Proteins are fairly big molecules. So you have your blood is gaining and losing things based on what you eat and drink, and your kidneys filtering your blood. Your cells are making things, they're breaking down molecules, they're making molecules, so they've got stuff going on in there. The interstitial fluid is just kind of this middleman between your cells and your blood, and it doesn't really have much control over what's happening to it. It's just getting whatever your cells and blood decide to give it, and it's losing whatever your cells and blood decide to take from it. Okay, the two that are the most similar are your interstitial and your blood. And the reason for this is because capillaries have holes. Remember, you've learned this. Capillaries have holes. You want exchange. You need stuff moving in and out of the blood at capillaries. And really, the only difference between the interstitial and the blood is the proteins. Everything else you notice is the same here. So all of this is the same. And the only reason that the proteins are a difference is because proteins are too big to fit through those holes. Okay, then if you look at sodium and potassium, notice they're kept separate. Potassium is inside the cells, sodium is outside, and that's because cells have sodium-potassium pumps. And those pumps are constantly moving sodium and potassium in opposite directions of each other. And just to point out, it's most of your potassium is inside here, and most of your sodium is outside. Not all. There is a little bit of sodium in cells. There is a little bit of potassium in extracellular fluid. So this is most, but not all. Okay, then if you look at calcium and phosphorus, those are also kept separate from each other. You have phosphorus inside, you have calcium outside. You purposely do this. You make sure you keep calcium out of your cells. So you also have calcium pumps here to keep the calcium out. You don't want calcium inside your cells. Well, think back to chapter 7 about bones. When calcium and phosphorus get together, they form hydroxyapatite, and that is what makes bones hard. Well, you only want your bones to be hard. You don't want all the other cells in your body to harden up. So they are kept separate to prevent the formation of hydroxyapatite all over your body. So you only want hydroxyapatite in your bones. Your bones are the only part that should be hard. You don't want your whole body hard like bones. Okay, so that takes care of the distribution of the fluid and the electrolytes. Now we're going to look at osmolarity. So this goes back to chapter 4. You learned about osmolarity in chapter 4. Remember you did the lab where you put a potato in salt water and we had the tube of molasses and the water came into the molasses. So that's what we're looking at here is osmolarity. This is basically how salty a solution is. And remember, salt, when you're talking about it in science, doesn't just mean table salt. So we're talking about solutes, things that attract water. So we're looking at the attraction of water. And remember back in chapter 4, you learned about isotonic, hypotonic, hypertonic, and how it's important to maintain that, because otherwise your cells would either shrivel up or explode because of the attraction of water in or out of them. So we're just first going to start off by looking at basic osmolarity. And I have beakers here set up, and we're going to have the top one is just going to be our standard for comparison. And I'm just going to use very simple numbers. So these do not represent the actual amounts of water and salt in your body. I'm just using simple numbers to make the point. We're going to say that here we have 10 water and 10 salt. That means we have a ratio of 1 to 1. 1 water for 1 salt. Now down here we're going to do different varieties of water and salt in the beakers and see how it compares to our standard. So we're going to start off, let's say we keep the water the same. We still have 10 waters, but we double the amount of salt. We have 20 salts. Well, now if you look at the ratio, you have 1 water, but you have 2 salts. So you made this saltier, right? If you add more salt, it gets saltier. Well, there's another way to make it saltier. We can also reduce the amount of water. So let's say we keep the salt steady at 10, but we cut the water in half to 5. Well, you still have that 1 to 2 ratio now. This is still saltier. In each case, whether you raise the salt or you reduce the water, your concentration of salt is higher now. You have saltier water. And this is increased osmolarity. And whenever you increase the osmolarity, you're going to attract more water. If it's saltier, it will attract more water. Okay, in the middle one here, we're going to keep a constant osmolarity. If we double the water and we also double the salt, nothing really changes as far as osmolarity. It's still a 1 to 1. If we cut both in half, if we only have 5 water and only 5 salt, again, it's still 1 to 1. We didn't change the osmolarity. So this is constant osmolarity. So if you change the water and salt together so that either they both increase or they both decrease, your osmolarity stays the same. Okay, now let's look at how we can reduce osmolarity. So we're going to make it less salty. Well, we can decrease the salt. If we keep the water the same, but we knock the salt down to 5, you now have 2 waters for every 1 salt. Or you can increase the water. So we can keep the salt steady at 10, but we can double the water. And again, you're going to have 2 waters for every 1 salt. So in both of these cases, we diluted the salt. We made it less salty. So this decreases the osmolarity. Anytime you reduce the saltiness, you decrease the osmolarity. And so this is now less attractive to water. So if you make something saltier, that increases the osmolarity and it is more attractive to water. If you make something less salty, you decrease the osmolarity and that is less attractive to water. Okay, so let's go through these questions. 2 ways to increase osmolarity. Well, you can increase osmolarity by increasing the salt, or by decreasing the water. Either of those actions will make it saltier. Two ways to decrease osmolarity. So now look over to the right. If you decrease the salt or you increase the water, you make it less salty. And osmolarity is not just the amount of salt, but it is the ratio of salt to water. Or you can think of it as the concentration of salt, right? If we start with a beaker with 10 water and 10 salt, and we add 10 salts to that, but we also add 10 waters, we didn't change the osmolarity, even though we added more salt. It's about the salt and water ratio, how they relate to each other. Okay, so now let's put that in context of cells. And again, this is going back to chapter 4. This is a review of chapter 4. We'll have 0.9 in each cell. That is the saltiness. A cell is 0.9% salt. So we're going to start off with, in the middle, we'll do isotonic. Okay, so remember, iso means equal. So this means we put a solution outside the cell that is also 0.9% salt. So this is a constant osmolarity. Neither one is any more attractive to water than the other, so water will stay put. And remember, this is what you want. Again, go back and review chapter 4. In your chapter 4 lab, this is where we covered this. You want water to just stay put. Let's suppose you have hypertonic. Remember, hyper means more. And remember, with these words, we're talking about the outside of the cell. That means the outside of the cell has more salt than the inside. So let's double it. Let's say 1.8. 1.8 is twice as much as 0.9. This means you have an increased osmolarity out here. And remember, if you increase the osmolarity, it is more attractive to water. So water will leave the cell. Because it wants to be with that higher osmolarity on the outside. And this causes crenation of the cell. So the cell will shrivel up. And this is bad. You don't want this. You'll die if this happens. And the example, if you remember back to chapter 4, this is if you drink ocean water. This is why if you're lost at sea, you can't drink the ocean water. Ocean water is 3.5% salt. That will make your blood very hypertonic. It'll draw the water out of your cells. Okay, let's look at the other end here. You could have hypotonic. So hypo means less. So let's say this is 0.45. 0.45 is half of 0.9. So if that is the case, you have a lower osmolarity out here in your extracellular fluid, your blood and your interstitial. That means the inside of the cell is more attractive to water. So water moves into the cell. And this will cause lysis. Your cell will explode. And this also causes cerebral edema. Causes the brain to swell. And remember, that can cause seizures and death. So if you relate this to our beakers, the way you would become hypertonic would be by adding more salt or reducing the amount of water. So like I said, with ocean water, it's 3% salt, 3.5% salt. That's adding salt. Or if you're not drinking so that you become dehydrated. So this would be if you add too much salt to your blood, or you fail to add water to your blood, you get dehydrated. Okay, this could also be like sweating a lot and not drinking to replace it. So it's true there is salt in sweat, but there's more water than salt. So when you're sweating, you have a net loss of water. And with the hypotonic, hypotonic, that would be the beakers over here on the right, where you are either you're diluting it by either adding too much water or you're not adding enough salt. So this would be like, for example, if you drink too much water. Remember in chapter 4, like the Wii for Your Wii, that contest the radio station had where you had to drink a bunch of water and then you won a Wii gaming system, and the woman who won died because she drank too much water and made her blood hypotonic. And this could also be from a very low sodium diet. Okay, so what happens if you drink too much plain water? Well, if you drink too much plain water, you will make your blood hypotonic. Because you will dilute the salt that you have in your water. You're adding water, but you're not adding salt with it. What happens if you sweat a lot or don't drink enough water? Well, in that case, you would make your blood hypertonic. Because remember, sweat is salty, but there's more water lost than salt lost. And IVs are 0.9% saline. Sometimes they're 5% dextrose. That's the other option, because that is what is isotonic. And this way your cells neither gain nor lose water, so they stay alive. Remember, if they gain water, they'll explode. If they lose water, they crenate. This chapter covers several electrolytes and maintaining balance of them. Right here, we're going to focus on sodium and potassium. So sodium, both of these have several responsibilities. We're just going to look at the main one. The main thing that sodium is responsible for is your osmolarity. Sodium has the biggest impact on the water in your body. So if you have too much sodium, and remember it goes by its Latin name, so this would be hypernatremia. Your blood would be too salty. And your extracellular fluids. So remember, your blood and your interstitial fluid pretty much stay equal to each other with the exception of protein. So your extracellular fluid would be too salty. So this would draw water out of your cells. And you would get crenation of your cells. If you don't have enough, that would be hyponatremia. This would mean that your extracellular fluid is too diluted. There's not enough salt. And this would cause water to enter your cells. And you would get lysis, and your brain would swell. we look at potassium, potassium has several responsibilities. One of the main ones is to repolarize your heart so that it can beat again. So think back to chapter 19. You had that cycle, -60 opens the sodium gates, sodium comes in, you go to -40, this causes calcium to come in, you go to 0, this causes potassium gates to open, potassium goes out, and you return to -60. Potassium is what repolarizes your heart. And this is what keeps it beating. If you have too much, that is hyperkalemia. So think about this, how that's going to affect the heartbeat. If there is too much potassium out in your blood. So remember, the potassium moves out by diffusion, which means you move from high concentration to low concentration. Well, if you have extra outside, then it's not going to diffuse out. You have to have the inside be the area of high concentration and the outside be the area of low concentration in order to get it to diffuse out. If you put extra on the outside, you stop that diffusion. You no longer have that high and low concentration areas. So hyperkalemia will stop the potassium from diffusing out of the heart. So now, because it's not diffusing out, your heart fails to repolarize. So you won't go back down to -60. So this means your heart just stops beating. If it doesn't repolarize, it doesn't beat the next time. So you have cardiac arrest. Okay, then let's look at hypokalemia. If you have hypokalemia, you lack potassium out here. Okay, so again, think about diffusion. This is inside's going to be your area of high concentration. Now outside is going to be very low. Remember, diffusion stops once it's equal. So if you lack potassium on the outside, even more is going to diffuse out. So you're going to have too much potassium diffuse out of the heart. So that's going to hyperpolarize. The more potassium diffuses out, the lower the voltage goes. So this will cause you to hyperpolarize the heart. So instead of -60, maybe it's -70. And when you hyperpolarize it, you make it so that the sodium can't get it up to -40. It's so negative, you let sodium in, but you don't quite reach -40. And if you don't reach -40, you're not going to open the calcium gates and the heartbeat is going to stop. So you hyperpolarized the heart so low that sodium can't raise it to -40. Maybe the sodium only raises it to -30 now, which isn't enough to open the calcium gates. And so again, cardiac arrest. So when it comes to potassium, either way, if you have too much or not enough, your heart stops beating. Okay, so then if we think about potassium injections, if you get too much potassium, somebody injects potassium into your blood, that is going to stop the diffusion of potassium out of the heart, and the heart will fail to repolarize and you will have cardiac arrest. Well, there's two ways we use this. This is how we execute criminals. Right? So lethal injection, it's a shot of potassium. Also, veterinarians use this when they put animals down. So, like if your dog is old and sick and you take him to the vet to have the vet put him to sleep, they give him a shot of potassium. Okay, insulin is going to affect your potassium. Remember, the whole point of insulin is that it moves nutrients from your blood into your cells. You get insulin after you eat. Well, potassium is one of those nutrients. So before in chapter 17, we talked about glucose and amino acids and lipids. It's also potassium. So every time you have insulin, potassium moves out of your blood and into your cells. So insulin has the effect of reducing potassium. So if you overdose on insulin, so this would be like someone who's diabetic and has to take insulin shots, it's very important to give them the right dose. If you mess up and you give them too much, so if you overdose on insulin, you will move too much potassium out of the blood. And this will cause hypokalemia. So then, because there's not enough potassium in the blood, too much diffuses out of the heart, and that makes the heart hyperpolarize, and the sodium can't raise it to -40, and you get cardiac arrest. And sometimes in the movies or TV shows, they'll kill somebody by giving them a shot of insulin. There's the movie The Accountant. It's a really good movie. And in that movie, the bad guys kill a guy because he's diabetic, and they break into his house at night and give him a shot of his own insulin, and he has a heart attack and dies. Okay, bodybuilders have to be careful of this. Remember, insulin moves all of the nutrients from your blood into your cells. And if you remember back to chapter 17, one of the things insulin does is it moves amino acids into your muscles and stimulates protein anabolism. So insulin makes your muscles bigger. So insulin moves amino acids into muscles and stimulates protein anabolism. So just look back to chapter 17 for that. This makes muscles bigger and stronger. So sometimes competitive bodybuilders will purposely inject themselves with insulin to help make their muscles get bigger. But this can backfire. It can be deadly because it can cause that hypokalemia. And that hypokalemia can cause cardiac arrest. Okay, pH is another important one. One of the biggest dangers of low blood pH is that it will affect your potassium and cause cardiac arrest. So let's look at how that happens. So you have your cell and you have your blood. So if you have low pH, that means there's extra hydrogen. So remember, a drop in pH means you have too many hydrogens. So that means we have a lot of hydrogen here in the blood. So the hydrogen is going to diffuse. You create a high concentration of hydrogen in the blood. So some of that hydrogen will diffuse into the cell where there is a low concentration of hydrogen. Now you also have potassium in your cell. Potassium and hydrogen are both positive. They're both cations. And remember, likes repel. So as all this hydrogen is diffusing into the cell, the potassium doesn't like it. It is repelled by all these other cations. So the potassium will leave the cell to get away from the hydrogens that are coming in. This causes then extra potassium in the blood. You get hyperkalemia. And if you have hyperkalemia, go back up here, if there's extra potassium in the blood, it won't diffuse out of the heart, your heart fails to repolarize, and you have cardiac arrest. So before you've learned about how changes in blood pH are dangerous because they can denature your proteins, now you know a second way that changes in blood pH are dangerous. So there's two things about blood pH that can kill you. One is it can denature your proteins. The other is that the hydrogen will diffuse into your cell, which drives the potassium out of your cell, which causes hyperkalemia in the blood, which makes the heart fail to repolarize, which causes cardiac arrest. Now we can move on and review some hormones. So this is all a review of what you've already learned in Chapter 20. So first we're going to look at the renin-angiotensin system. So remember, you have your liver makes angiotensinogen. So this is an inactive hormone that is made by your liver, and it is kept in your blood all the time. So you always have angiotensinogen in your blood. Your kidney is in charge of activating it. Your kidney is monitoring your blood pressure, and it will detect when you have a drop in blood pressure. So if your blood pressure gets too low, your kidney's going to know. Also, your kidney responds to norepinephrine. So if you have an adrenaline rush, your kidney's going to know about that also. Either one, a drop in blood pressure or norepinephrine, will cause the kidney to secrete renin. Renin is an enzyme. And renin converts angiotensinogen to angiotensin 1. Think of angiotensinogen like a can of SpaghettiOs. It's sitting in your kitchen cabinet. It's just there waiting for when you need it. It's inactive. Renin is the can opener. When you need your SpaghettiOs, it's time to eat lunch, you have to get your can opener out to open that can and access your SpaghettiOs. So renin is the enzyme that converts angiotensinogen to angiotensin 1. Okay, now hopefully you're not just going to eat cold SpaghettiOs straight out of the can. You're going to put them in the microwave and warm them up. So we have another step here. Angiotensin 1 is not quite ready to go. It has to flow through the lungs. And your lungs have an enzyme called angiotensin converting enzyme, which we can just call ACE. So this is another enzyme. Let me put this in a different color. Your lungs have ACE, angiotensin converting enzyme. That converts angiotensin 1 to angiotensin 2. So this is now your SpaghettiOs come out of the microwave. They're hot. They're ready to go. Now you have to get your synergistic partners. Remember, some hormones have synergistic partners. Angiotensin 2 is your active hormone. But it doesn't work alone, right? So maybe SpaghettiOs is not a whole lunch. Maybe you want to have a grilled cheese sandwich with it and something to drink. So you have to get your synergistic partners. So it's going to go to the hypothalamus, and it's going to tell the hypothalamus to stimulate the posterior pituitary to secrete ADH, antidiuretic hormone. It's also going to go to the adrenal cortex, and it's going to stimulate the adrenal cortex to secrete aldosterone. Now you have a group of 3 synergistic hormones. You have angiotensin 2, ADH, and aldosterone. Now remember, the stimulus and the effect have to match up. Our stimulus was low blood pressure or norepinephrine. So if your problem is that your blood pressure is too low, the solution is to raise the blood pressure. And whenever you have norepinephrine, if you remember that, sympathetic raises blood pressure. So they are going to act to raise blood pressure. So now that chart at the end of chapter 20 is going to come in handy. How do you raise blood pressure? Well, one thing we want to do is increase blood volume. So remember, the more blood volume you have, the more blood pressure you have. So we're going to increase blood pressure by increasing blood volume. We want more water in the blood. We can also increase resistance in your vessels. So again, reference that chart you have at the end of chapter 20, things that raise and lower blood pressure. That's what we're doing here. So our hormones are going to go to your glomerulus. So remember, this is the nephron. This is where you're making urine. They're going to constrict your afferent arteriole and your glomerulus. So build on what you learned in chapter 24. If you do this, you will decrease your net filtration pressure. This will reduce the amount of filtrate you make, which will in turn reduce the amount of urine you make. So you are taking less water out of the blood up front. Remember that 180 liters you take out per day? You are reducing that. So this reduces the water removed from the blood. Another thing you're going to do is get more sodium potassium pumps. So down here at the end, we're going to have more sodium potassium pumps. That's what the aldosterone is going to do. These pumps, think back to chapter 24, are going to move sodium into the blood. And water follows sodium. Remember, we just talked about how sodium's main job is to attract water, maintain osmolarity. So now you have more sodium and more water in your blood. The ADH is going to give you more aquaporins. And remember, these are going to move water into your blood. So the result here of the more sodium potassium pumps and the more aquaporins is you're going to have more water return to the blood. And you're going to have less water go to the urine. So by reducing the amount of water you take out in the first place, and then by putting more of that water back into the blood, you increase your blood volume. Okay, another thing we're going to do, I'm going to go ahead and switch to another color for this, is stimulate the hypothalamus. If you remember back to chapter 13, the 7 jobs of the hypothalamus, one of those is thirst. So you're going to stimulate your hypothalamus to be thirsty. This will then cause you to drink, and when you drink, you will increase your blood volume. Then we're going to act on a blood vessel. We're going to cause vasoconstriction. And remember, ADH, when it's causing vasoconstriction, it can be called vasopressin. So vasopressin and ADH are the same thing. And when you cause vasoconstriction, you increase resistance. And increasing resistance increases blood pressure. So that is how the renin-angiotensin system is going to work to increase the amount of volume in your blood and increase the resistance in your vessels and increase blood pressure. So the effect, if we summarize it, the effect on body fluid is it increases your body fluid. Okay, then if we look at antidiuretic hormone independent of this, so ADH can be part of the renin-angiotensin system, but it doesn't always have to be. It can also be its own independent thing. So remember, ADH comes from the posterior pituitary, which is controlled by the hypothalamus. Your hypothalamus monitors your blood osmolarity. Okay, so remember, this is the concentration of salt in your blood. It's not just the amount of salt, it's the ratio of salt to water. Your hypothalamus is monitoring this. And anytime your osmolarity gets too high, so this would be like if you eat lots of salt, or if you fail to drink. That's going to increase the osmolarity. So it means your blood is too salty. It's going to stimulate your posterior pituitary to secrete ADH. So now we're looking at ADH when it's being secreted because your blood is too salty. ADH is going to cause you to have aquaporins. And remember, aquaporins are going to move water alone to your blood. So you will have more water going to your blood. You will therefore have less water in your urine. And ADH acts on water alone. It has no effect on salt. So because you're adding water, but you're not adding salt, you reduce the osmolarity. So you fix that problem of your blood being too salty. ADH is also going to come back around, we make a full circle here, and it's going to stimulate your hypothalamus to be thirsty, so that you will also add water to your blood by drinking it. And remember, ADH can also be called vasopressin because it will cause vasoconstriction. Okay, then aldosterone. So aldosterone is part of the renin-angiotensin system, but it can also act independently. Aldosterone is from the adrenal cortex. And your adrenal cortex monitors your blood potassium and sodium. if your potassium is too high or your sodium is too low, then it secretes aldosterone. So remember, the solution matches up to the problem. The problem is that your potassium's too high or your sodium's too low. Aldosterone makes your nephron have sodium-potassium pumps. These are going to put sodium into your blood. And they're going to put potassium into your urine. So they're fixing that problem. Your potassium was too high, so you're getting rid of potassium in your urine. Your sodium is too low, so you're putting sodium back into your blood. And remember also that wherever sodium goes, water follows. So whenever you have aldosterone, you gain sodium and water into your blood. You lose potassium through your urine. Then we have ANP. This is atrial natriuretic peptide. This comes from your heart. It is when your heart is overstretched by too much blood. So the problem is you have too much blood. That means you want to get rid of some of it. Well, the way you get rid of it is by having the kidneys produce more urine. So ANP, the first thing it's going to do is shut down your renin-angiotensin system. So you can imagine this as renin-angiotensin, and the foot is ANP, because it wants to do the opposite of what renin-angiotensin system does. So ANP is going to inhibit the reabsorption of sodium into the blood. So you're going to block sodium from coming back into the blood. That means you will lose sodium in the water or in your urine. And if you lose sodium in the urine, water follows. So you're going to have more urine production. You're going to take sodium and water from your blood and lose them in the urine. You're also going to cause vasodilation. You want to reduce the resistance and get some relief on all that blood going into the heart and stretching the heart. Okay, so some things to look at here. The hormone that always goes out with its friends, that is angiotensin II. Anytime you have angiotensin II, you also get ADH and aldosterone. The hormone that reduces osmolarity is ADH because it causes you to get water alone. You don't get salt with the water. The hormone that maintains osmolarity is aldosterone because it causes you to get sodium and then water follows. So you're gaining both sodium and water in your blood. And the hormone that counteracts the other three is ANP. So it's kind of notice all these hormones start with an A. You have angiotensin II, antidiuretic hormone, aldosterone, and atrial natriuretic peptide. Three of them are all doing the same thing. Angiotensin, ADH, and aldosterone are all increasing the amount of blood volume and blood pressure. ANP does the opposite. It reduces the blood volume and blood pressure. And if you eat a bag of chips while sweating on a hot summer day, which hormone will you get? Well, think about chips are salty, So you are adding salt to your blood. When you sweat, you lose both water and salt, but you lose more water. Sweat is mostly water with a tiny bit of salt. So if you're eating chips and sweating, you are increasing your blood osmolarity. And remember, your hypothalamus will detect this, and it will stimulate your posterior pituitary to secrete ADH. ADH will give you aquaporin. You will reabsorb water alone. ADH will also go back and stimulate the hypothalamus to be thirsty, and you'll drink some water. Now we can look at pH. And again, most of this is going to be review. You learned about pH first in chapter 2, and we've talked about it several times since in other chapters. So remember, your ideal pH is 7.4. And your safe range is 7.35 to 7.45. So as long as you're in that range, you're safe. If you go below that range, so acidosis would be too much hydrogen in your blood. And alkalosis would be not enough hydrogen in your blood. So in either case, if pH is too low or pH is too high, you run the risk of denaturing your proteins. So that goes for both of them. Then remember, we also talked about how if pH is too low, you will have hydrogen enter your cells, and the potassium will be repelled and it will leave, and you will get hyperkalemia, which will lead to cardiac arrest. So this section is going to focus on how you keep your blood pH at 7.4. And you have two things here we're dealing with. We're going to be dealing with hydrogen ions, and we're also going to be dealing with bicarbonate. Bicarbonate is important because it binds hydrogen. Bicarbonate is a buffer. And if you remember, if you go back to the very first page of chapter 25 where we have that box, remember you have a lot of bicarbonate in your blood in your interstitial fluid. So suppose you had a bunch of hydrogens and there were too many of them. A bicarbonate will come along and it will bind a hydrogen. So we started off, we had 3 hydrogens floating around. A bicarbonate will bind one of those, and now you have 2 hydrogens floating around. So bicarbonate is very important because it binds your hydrogen. So as long as you have a balance of hydrogen and bicarbonate, your pH will be 7.4. If you lose bicarbonate, then it's not there to bind hydrogen. And if it's not there to bind it, you'll have too many hydrogens floating around. Back over here, we started with 3 hydrogens. We had a bicarbonate bind one of them. Now we have 2. If the bicarbonate's not there, you would still have 3 floating around, which would be too many. So if it's not there to bind the hydrogen, you will have too many hydrogens. And this will cause a drop in your pH, which would be acidosis. So that's the importance of bicarbonate. It binds hydrogen and prevents acidosis. If you lose bicarbonate, your pH goes down. So now we're going to look at what's going on in your body that would cause changes in your pH. So first we'll look at pH decreases. So remember, if pH is decreasing, this means you're increasing the amount of hydrogen. you are adding acid to your blood. So the things that do this are your diet, and especially meat and wheat will add acid to your blood. Cell metabolism. And remember, metabolism refers to all chemical reactions, not just making ATP. So as your cells are doing their normal thing, they add keto acids, phosphoric acids, and lactic acids to your blood. So your cells add acid to your blood. Then here, notice we have an arrow going away from the blood. That would be loss of bicarbonate. Because remember, if you lose bicarbonate, it's not there to bind the hydrogens, and so you end up with more hydrogens floating around. This happens through diarrhea. So diarrhea has bicarbonate in it, and if someone's having diarrhea, they're losing bicarbonate, which makes their blood pH go down. Okay, then we can look at blood pH increase. So blood pH is increased. This means you have fewer hydrogens. This could be from a vegetarian diet, or if someone has heartburn and they're taking antacids. So now you're adding base to your blood, and this base is going to bind your hydrogens. Then we have an arrow here going away from the blood, which represents a loss. This would be if you vomit. When you vomit, you lose your stomach acid. Stomach acid is hydrochloric acid, HCl. Anytime you vomit and you lose that, your stomach has to make new. And one of the ingredients is hydrogen. So your stomach has to take hydrogen from your blood in order to make new acid. So vomiting makes you lose your stomach acid. Your stomach makes new acid by taking hydrogen from your blood. This reduces the amount of hydrogen in your blood and raises your pH. So vomiting can cause alkalosis. It can make your pH too high. So these are the things going on that would alter your pH, and your body is constantly having to fight to keep your pH at 7.4. So maybe not so much fight, but work. Your body constantly works to counteract these activities. And keep your pH at 7.4. So now we're going to look at the ways your body counteracts these things that are constantly going on. So you're always eating either meat or wheat or vegetables, and you're altering your pH. Sometimes you might take an antacid, you alter your pH. Your cells are doing metabolism, they're putting acid in your blood. People get sick sometimes, have diarrhea or vomiting, that messes up pH. So your body is constantly working to keep it 7.4. So the first thing you have to keep your pH at 7.4 is your buffers. And you first learned about these back in Chapter 2. So review your Chapter 2 lab. Buffers can bind or release hydrogen. And they do this to keep pH at 7.4. So they prevent changes in pH. So if you have too many hydrogens. Your buffer will bind some. If you have not enough hydrogens, your buffer will release hydrogens. So they can do either one. They can bind hydrogen or they can release it to make sure that you always have just the right amount of hydrogen. Buffers are found in your interstitial fluid, your blood, and your intracellular fluid. And this relates to that box at the first page in notes. So go back and look at that box. Inside your cells, you have protein. So you have protein buffers. And inside your cells, you have phosphate. So we have phosphate. So inside cells, protein and phosphate act as your buffers. In interstitial fluid, you have bicarbonate. So that's your main buffer. And in blood, you have bicarbonate and protein. So those are the buffers. And notice the clock here. This clock is showing us a small amount of time. Buffers work immediately. They are fast. So as soon as the number of hydrogens change, the buffer immediately responds to restore your number of hydrogens. But they are also the weakest. They have a very limited capacity. And you might remember that from your Chapter 2 lab. So they are fast, but they have a limited capacity. They can only bind so many hydrogens and they only have so many to give. So you can overwhelm your buffers if you make big changes in your hydrogen. Then we get to physiological buffers. So you have two of these. Your physiological buffers are what actually remove hydrogen from your body. So the buffers are just binding. It's temporary. Physiological are a permanent solution. They actually get rid of stuff out of your body. So your first physiological buffer is your lungs. And you already know all about this. We've been talking about it since Chapter 3. Remember, here's your mitochondria. And your mitochondria makes ATP. And while doing so, it also makes carbon dioxide. And it puts that carbon dioxide in your blood. And remember, carbon dioxide reacts with the water in your blood to form carbonic acid. That chemical formula, just to review, that's what happens when you put carbon dioxide in your blood. It makes acid. So you rely on your lungs to exhale carbon dioxide. And when they do, you reverse this chemical reaction and you get rid of, you put that hydrogen back into the water. So your lungs remove acid from your blood by exhaling carbon dioxide. And we talked about this a lot in Chapter 3 and just recently in Chapter 23. So hopefully this is soaking in by now. Your cells, when they make ATP, they also make carbon dioxide. That carbon dioxide combines with the water in your blood to make acid. but then your lungs reverse this by exhaling the carbon dioxide, and that forces the hydrogen back into the water where it originally came from. And that reduces the amount of hydrogens floating around in your blood. And if you notice the clock here, this is a little bit slower, but it is also more powerful. So it is slower than buffers, but more powerful. You're not just binding, you're actually removing from the body. Okay, then we go to your kidneys. So this is a review. You just learned this in chapter 24. Your kidneys have the type A cells and the type B cells. So the type A cells are these on the top. And here you have, this is your blood, and this is urine. And remember, they're going to move bicarbonate and hydrogen in opposite directions. So type A cells are going to put hydrogen in the urine, and they're going to put bicarbonate in the blood. And this will raise your pH. So the type A cells get rid of hydrogen in your urine. And this is the most common. This is what most people are doing. So by getting rid of hydrogen in the urine, you raise your pH. But then you do also have the type B cells. There's your type B cells. They're going to do the opposite. They're going to put the bicarbonate in the urine and the hydrogen in the blood. This is rare. Not very many people are doing this. It would mainly just be vegetarians that are doing this, or maybe somebody who's taking a lot of antacids. And if you notice the clock here, the whole clock's filled in. This is a very slow process. It takes several hours or even days for your kidneys to have an effect on your pH, but it is the most powerful. They can make the biggest adjustment to your pH. So if we kind of put all this together here, you have your cells. And this is more of a simplified, but in general, for most people, your cells are putting acid into your blood. So this middle box here represents your blood. In general, for most people, you have this constant flow of acid into your blood. So your first line of defense is your buffers. Your buffers are going to bind it and prevent changes, but that's just a temporary solution. You still have to get rid of it. Think of like if you spill your drink on the table and you use a sponge and you soak up the spilled drink. The sponge is like the buffer. It's there and it kind of sops up the spilled drink from the table, but that's not really solving the problem. You still have your Pepsi, it's just in a sponge now. You have to take the sponge over to the sink and wring it out to actually get rid of it. So then you have your lungs and your kidneys that are going to actually get rid of it. And remember, acid comes in two types, fixed and volatile. So the volatile acid, which is CO2, will be removed by your lungs. And the fixed acid, which is all the others, will be removed by the kidneys. So in general, for most people, your cells are putting acid into your blood. Your buffers are temporarily binding it until your lungs and kidneys can get rid of it. Okay, so some summary questions here. The fastest is your chemical buffers. They work immediately. The most powerful is your kidneys. And the locations of the buffers to that rectangle that we had on your first page of notes. So remember, in your cells, we have phosphorus, so you have the phosphate buffer, and you have protein. Then your interstitial has bicarbonate. Then your blood has bicarbonate and protein. And which type of acid do the lungs eliminate? That is volatile. And remember that kidneys eliminate fixed, and buffers are binding or releasing hydrogen in order to keep the number of hydrogens steady. Okay, now we can look at compensation. So remember, you have your lungs and you have your kidneys. These two organs are what remove acid from your body. So your lungs and your kidneys are what actually remove acid. So they're kind of like a team. And whenever one of them slacks, the other picks up the slack. So that's compensation. If one slacks, the other picks up the slack. So if we look at the lungs first, and this ties into what you've learned in chapters 23 and 24. We're just kind of putting it together here. But remember in 23, we talked about respiratory alkalosis and respiratory acidosis. So let's say you breathe too much. Right? You're hyperventilating. If you breathe too much, you lose carbon dioxide, which means you lose acid from your blood, which makes your pH go up. And so you would have respiratory alkalosis. You need to then retain some acid in your blood. So your kidney would compensate for this by retaining acid in your blood. So in this case, your volatile acid would be low, right? You don't have enough carbon dioxide. Your kidney makes up for this by causing you to have high fixed acid. Okay, so to kind of explain this, let's say you have 2 volatile acids and 2 fixed acids, so that your total acid is 4. If volatile acid is low, you only have 1 volatile acid. Your kidneys would retain some fixed. So now you have 3 fixed. You still have a total of 4. So as long as you have a total of 4, your pH is 7.4. Now that 4 is just a made-up number. The point is you have to keep the total acid the same. So if one is too high or too low, you adjust the other so that your total comes out the same. Let's keep going with this. Let's say you're not breathing enough. If you're not breathing enough, you will retain carbon dioxide. So you're going to have high volatile acid. So now let's give you 3 volatile acids here. That means you have respiratory acidosis. You're going to have your pH is going to be low, and you have respiratory acidosis. So what are your kidneys going to do to compensate for this? Well, your kidneys will get rid of more fixed acid. So now you'll only have one fixed. So that, again, your total is 4. Right? You're always wanting to keep that total the same in order to keep your pH 7.4. So if your lungs are messing up, your kidneys will compensate. If you were supposed to have, if this top one is what you should have, say you're supposed to have 2 volatile, 2 fixed for a total of 4. Your lungs mess up, you only have 1 volatile. Your kidneys will give you 3 fixed, so you have a total of 4. Your lungs mess up, you have 3 volatile. Your kidneys will compensate and give you 1 fixed, so you have a total of 4. It can go the other way also. Your kidneys can be the ones that mess up. Let's say that you have too much fixed acid in your blood. This is called metabolic acidosis. So this could be from kidney failure. It's very common in people with diabetes. Remember in chapter 17, if you have diabetes, you get too many keto acids because you're breaking down fat since you can't use glucose. And if you have, so like someone with diabetes makes a lot of keto acids, and it can be more than the kidneys can handle. And they can't keep up with getting rid of all those keto acids, and the keto acids build up, and you get metabolic acidosis. So this would be where you have too many fixed. So your lungs are going to respond by getting rid of more volatile. So your compensation now is to breathe more. So you're going to get rid of extra carbon dioxide. So now you would only have 1 volatile instead of your standard 2. And that brings you to your total of 4. And this you can see, this is called Kussmaul breathing. And you see this a lot in people with diabetes. So someone who has diabetes might just be sitting in their chair watching TV, totally relaxed, but they're breathing heavy like they're running a marathon. The reason they're breathing heavy is because their body is making so many keto acids that their kidneys can't keep up, their blood pH is falling, so their lungs compensate for this by getting rid of extra carbon dioxide. So they're making their volatile acid very low in order to compensate for the high fixed acid and keep the blood pH at 7.4. And the final scenario, you can lack fixed acid, right? You don't have enough fixed acid. So it could be for some reason the kidneys are putting too much acid in the urine, or it could be something else going on, like vomiting, where your stomach is then grabbing hydrogens from your blood. For whatever reason, there's not enough fixed acid. This is metabolic alkalosis. So your fixed acid is too low. You only have 1 instead of 2. So now your lungs are going to compensate by breathing less. And if you breathe less, you will retain carbon dioxide. So now you're going to have extra volatiles so that it gets you back to that total of 4, and you keep your pH at 7.4.